Yes.
Oh, very good. So, yeah, I'm not supposed to be here as being a program committee, but I'm just replacing a colleague of mine who has, we have been working on a topic together, and unfortunately he's been sick the last 2 days, which also means we will reach there in the end. He has not managed to completely complete the experiment. But I will get you as far as we went with that. So, a quick introduction. I'm representing here in Atera Nanosystems, which is a small startup. Well, actually it has become big recently, the last couple of years, which is a spin-off, a child of TU Delft. And it has grown to have about 100 employees now, so it's not a small company, it's more like a medium company. The market that they are targeting, what they are kind of where they are stepping in is essentially the world of sensors and IoT sensing. And what they're entering this market with is essentially a microcontroller, which is a neuromorphic microcontroller. Actually, it's not only neuromorphic. The goal there is practically to use input data from sensors, fuse them together, and essentially do all sorts of AI-related tasks at a very, very, very small power budget. And that's essentially what the product has been aimed at, essentially to come down to this space here, which is essentially less than 1 milliwatt power consumption. Yeah. Now, what's in this product, essentially, it's called, there has been a few generations, the latest of which is called C1 Pulsar. And what you have there, essentially, is 2 arrays of spiking neurons. One is analog, one is digital. You have a CNN, a small CNN accelerator. You have a RISC-V microprocessor. And then you have all sorts of interfaces and a couple of dedicated DSP accelerators. So you can think of it more or less like a kind of Swiss Army knife for playing close to the sensor. Yeah. Now, the topic I want to touch upon, unfortunately I don't see the time, but you keep track of it. You ring the bell. The topic I want to touch upon is essentially, I don't know if you're familiar with synaptic delays. So essentially synaptic delays is a principle that is coming, or a concept that is coming from cognitive neuroscience. It has to do with the fact that we can imagine the neurons, the synapses of a network having state and doing essentially a little bit more than just propagating at instant time, essentially activations from one layer to the next. It's a topic that recently has been receiving a lot of attention, and actually it's not the first time, it has happened several times in the history. It started back in the 1990 already from Hinton himself. It's just that recently the key thing is that a lot of works have emerged that has shown that we can start training, we can parameterize the neural models with delays, and we can train the delays practically, rather than just playing and manually fixing them in a model, which means we can scale up in size and we can start playing with deep models and these kind of things. Now, what's coming out from the literature so far, both the long-term history and the recent history, is that essentially delays is another temporal parameterization that we have in neural models next to, for example, decay, for instance, and recurrence. They help training, so essentially they help us get rid of the problem that we have in recurrent neural networks with exploding and vanishing gradients. Training is also faster from what has been reported in literature. and we have a substantial boost in performance. Yeah, so this thing is something that's been recorded in all the resurgences of this concept, and these are essentially the things that we have been coming up in recent literature. Yeah, the boost in performance actually is substantial most of the times. Now, you would think that essentially being a kind of neuromorphic concept or coming from cognitive neuroscience, it would have to do with efficiency, but the sole reason it has not been heavily adopted over time is actually because in the minds of the people this does not seem to be very efficient. Yeah, the way you would implement memory in a neural network is to put memory delays. You would put memory in synapses, and practically synapses is the resource which does not scale very well with the size. Yeah, so people see the benefit, but when it comes to efficiency, it doesn't seem on first sight to be very efficient or to boost efficiency. And so this is the thing that we wanted to explore a little bit. And where we are coming from is, as I said, with Pulsar, which is a chip that is extremely resource constrained. And so efficiency is paramount there. And we don't have resources to invest essentially to put memory for every synapse. Yeah, and so that was the motivation. And so we started experimenting with the benchmark. We thought that's the best way to do, like being in the industry now. We took MLPerf Tiny, the keyword spotting benchmark, which practically the benchmark, the baseline for that benchmark is depth separable convolutions with CNNs. And it sets a baseline at 90%. Yeah? So this benchmark has two tracks. It has the open and the closed track. The closed track, you have to stick to this model, and you have to run it on your own accelerator and record performance like energy and latency. The open track allows you essentially to use custom models. So it allows you to depart from this model here, so long as you can respect this accuracy. Yeah, so if you come up with a model that gets to that accuracy, it's okay to use it to measure essentially performance, hardware performance. Now, this is what's the state of the art with this benchmark at the moment. A question? No, sorry. So the state of the art, essentially, this is not exhaustive, but essentially this has the best models I could find in the literature so far. You can see that the accuracy is going actually way above 90%, but at the cost of very deep models. Well, very deep, nothing like inception models, but deep by the standards of neuromorphic models at least. And you can only push back the depth only if you go to very sophisticated neuron models. What's more to it is that these models have, of course, a lot of parameters, and you have to use things like attention mechanism, for example. You have to use separable convolutions, you have to use SSMs and these kind of things. So that's another thing to show that it's an interesting topic for neuromorphic systems, for neuromorphic accelerators. These are numbers that we have seen essentially not exactly with the benchmark, but with this task. So these results are not on the MLPerf Tiny, but it's with keyword spotting on neuromorphic accelerators. And essentially, what's the energy per inference that they can reach? So essentially, that's to say that it is, at least for a sensor company like Inatera, it's a very interesting thing, and it's very interesting for neuromorphic processing. Yes. So, getting to the experimentation, a starting point was to see how much we can do with small models, and we start without having any synaptic delays. And so practically we try models that have only leaf models that have, we can adapt the weights, and we played also with a p-leaf model, which PLIF essentially has a trainable also time constant. So every neuron can have its own trainable time constant. Yeah, and so this is the validation and test set. So the benchmark comes with training set, validation set, test set. And so these are the results that we could see essentially by using 2 or 3 layers of neurons with 128 and 512 neurons. And practically we did the same thing with recurrent DNNs. And what you see, the bottom line is like where I have black, bold face here is essentially which models can get above the baseline for the benchmark. And this is essentially the parameters that are reported. Yeah, so you can already see that with neuromorphic type of systems, we actually go to lots of parameters compared to GRU and LSTM, for instance, and actually quite big models. It's 3 layers, but it's quite many neurons there. So then the next thing we did is we said, okay, let's start deploying delays now. Yeah, so this is what we could achieve with leaf neurons. That's from the previous slide. Practically with neurons that have no delays, no synaptic delays, exponential leakage, and that's the baseline that you get. And more or less, if you start training a model with this parameterization, you will not very easily get to the 70%. Yeah. Then we added synaptic delays. We had exponential decay and we have linear decay. That's just because linear decay is what's supported on the Natera chip, which is it's a bad compromise. It's not such a good idea. Let's put it this way. Fixed delays where we don't train them, or trainable delays. And what you can see is actually that with 1 layer, 2 minutes only left? Shit. Sorry. We could get practically to the baseline performance. Yeah, so that's what you see here, which was very encouraging to continue, essentially the exploration. So the next thing we did is we tried to see what's the impact of depth of layers and breadth of layers. So what you see practically here is when we have 1, 2, 3, 4 hidden layers, and here what you have is like different breadth of these layers. And what comes out of this as a resume is that actually depth, when you're employing delays, does not matter so much. What matters more is the breadth. Yeah. So what you see here is that already from the second layer we don't see an improvement, but there is an improvement as we increase the width of layers. The other thing is about the time step size, the DT, practically of the system, and what we can see. Here, so you have 2 layers of 128, 512, 512, 3 layers, and what you see practically is that when you increase the DT, the time step size, so when you have less time steps, actually you start suffering, but not so much. The opposite is happening with the spikes. So practically, as you reduce the number of time steps, you have less spikes. So you lose some accuracy, but you have less spikes, which means you're more efficient on the compute side of things. The most interesting thing of all is the fact that what you have here is that you don't have to use delays in every layer. Yeah. So practically what you have here, what these lists mean is in a 3-layer network of 112, 28 or 512 neurons, one is where we deployed the synaptic delays. So here there is no synaptic delays. Here it's only in the output layer, the one before the output layer, the second layer, the first layer, and so forth. The very nice thing is that you see that immediately we get to the top performance we could reach with only employing practically the delays in the first layer. We have a problem every time we go to the last layer. Wherever we have delays in the last layer, there is a training instability there. So the cues that come out of this is that synaptic delays at the last layer are not very helpful, and only in the first layer gives you pretty much 90% of the benefit you are to have. So this was very good news for us, because this means that actually if you decide to use that parameterization, you don't have to make it a function of the number of synapses. Yeah? If you deploy them only in one projection, and practically if you use the smallest one, you have already huge benefit there. And then we had some other practically explorations where we check the sparsity. So if you don't have delays even in one projection layer, if you put some block sparsity structure there so that you don't have to have in each and every synapse. And so what you see in one side is when you have it as axonal delays, when you have synaptic delays, and this is a block structure in between, where you see again that there is a trade-off there. So the last thing we did, of course, is we took one of these models, which had only two hidden layers of 128 neurons. Linear decay, which is not a very good idea compared to having exponential decay. Axonal delays, which means we divided by 2 for every layer, so it's not a function of the number of synapses, but half of the synapses, and only in one layer. Now, this is extremely, extremely small compared to the depth separable convolution, which is the baseline of the MLPerf, yeah, which is like a 6-7 layer model, and it has lots of parameters, yeah, and we managed to get to that accuracy, of course, with PyTorch, and this is the test on the chip. We practically we just lose like 0.7 kind of points of accuracy. And the part which is missing from Simeon, and I apologize for that, is the energy numbers and the cycle count, which is essentially what he was supposed to measure in the last couple of days. Okay, and I think I'm done. I hope I'm not too much. Just 2 minutes, okay. Yeah, okay. Thanks very much.
During the coffee break we can ask, and can come back at 3:45.